What if everything you've ever seen is only a tiny illusion of what the universe really is? What if most of existence isn't filled with galaxies, but with something far more unsettling: emptiness? Tonight we're uncovering the hidden structure of the cosmos and the massive void we didn't even realize we were inside. A discovery that doesn't just change space, it changes where we stand in it. Now let's begin. If the universe were a colossal building, what percentage of the floor space do you think matter actually occupies? Think about everything you have ever seen when you look up at the night sky. Every star that has ever burned bright enough to catch your eye. Every galaxy photograph that has left you breathless, those sweeping spirals, those elliptical giants glowing at the centers of deep field images. Every nebula, every planet, every comet, every cloud of interstellar gas stretching across light years of space. Now imagine gathering every single one of those things. Every atom that has ever participated in the formation of a star. Every molecule that has ever been fused in a stellar core. Every wisp of hydrogen drifting between galaxies and piling it all into one accounting. You would expect that sum to be enormous. You would expect it to fill the universe in some meaningful, satisfying way. It does not. All of it, every star, every galaxy, every planet, every nebula, every structure that astronomers have ever catalogued across the entirety of the observable universe, occupies somewhere between 10 and 20% of the total volume of space. The other 80 to 90% contains almost nothing, not a little less than average, not modestly underpopulated, almost nothing. The universe measured honestly and in full is overwhelmingly, almost incomprehensibly empty. This is the number nobody wants to hear, not because it is frightening in an immediate personal sense, but because it contradicts something so deeply embedded in the human relationship with the cosmos that most people have never thought to question it. We have always assumed, without quite saying so, that the universe is fundamentally a place of things, of matter, of structure, of objects that can be named and counted and photographed. The emptiness in this intuition is just the background, the negative space between the real content, the way silence fills the gaps between notes in a piece of music without being the music itself. That intuition is wrong. The silence is the music, the emptiness is the content. And the structures we celebrate, the galaxies, the clusters, the cosmic web of filaments and walls, are the gaps in the emptiness, not the other way around. To understand why this truth took so long to surface, consider what a photograph of deep space actually shows you. The most famous example is the Hubble Ultra Deep Field, an image assembled from hundreds of hours of exposure time pointed at a patch of sky roughly the angular size of a tennis ball seen from 40 meters away. In that image, approximately 10,000 galaxies are visible, stacked across billions of light years of cosmic depth. The image looks crowded, it looks abundant, it looks like a universe overflowing with structure packed from edge to edge, with luminous objects competing for space in the frame. But here is what the image does not show you: the overwhelming majority of the volume between and around those galaxies. A telescope collects light, its sensors register photons. Wherever photons arrive in sufficient numbers, a bright point or smear appears in the final image. Wherever photons do not arrive because there is nothing there to emit them, the sensor registers nothing, and that nothing appears as black in the final picture. The image you see is not a representative portrait of the universe. It is a map of where light originates, which is a very different thing from a map of where space exists. Think of it this way. Imagine a soaked newspaper lying on a table. You look at the surface and see dense columns of text, headlines, photographs, advertisements, ink covering what appears to be most of the surface. But the newspaper is 90% water. The ink, the actual content that draws your attention, is a thin layer printed on a medium that is almost entirely something else. When you look at a deep field astronomical image, you are looking at the ink. The water, the vast, lightless expanse of space that constitutes the actual volume of the universe, is invisible to you, not because it is not there, but because your instrument was designed to find the ink. The consequence of removing this optical bias is a number that the human mind resists absorbing: roughly 80 to 90% of the observable universes. Volume consists of regions called cosmic voids, zones where the density of matter falls so far below the cosmic average that they are for almost every practical purpose empty. Not the emptiness of a clean room or a quiet field. The emptiness of hundreds of millions of light years containing fewer galaxies than a modest galaxy cluster would hold in a volume 1,000 times smaller. If you were to select a random point in the observable universe, not a point near any galaxy, not a point biased toward any known structure, but a genuinely random coordinate drawn from the full three-dimensional volume of observable space, the overwhelming probability is that your point would land inside one of these voids. You would find yourself surrounded by darkness extending in every direction for distances so vast that the nearest substantial galaxy might be hundreds of millions of light years away, no stars visible to any naked eye, no galactic disk spreading across the sky, nothing but the faint cold afterglow of the Big Bang and the slow expansion of space carrying the distant walls of the void ever so slightly further away. That is the typical location in the observable universe. Not the crowded node of a galaxy cluster, not the middle of a spiral galaxy arm, a void, a near emptiness that stretches further than any human civilization has yet managed to think clearly about. And of all the voids in the observable universe, the one most immediately relevant to every measurement, every observation, and every cosmological model that human science has ever constructed is one that was confirmed only in the year 2013. It is called the KBC Void, named after the three astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who compiled the evidence that forced its recognition. It spans approximately 2 billion light-years in diameter. It is centered more or less on our position in the cosmos. The Milky Way, along with the entire Laniakea supercluster, containing roughly 100,000 galaxies across 520 million light-years, sits inside it. We are not observers looking at the void from the outside. We are inside it. We have always been inside it. Every telescope we have ever built, every photon we have ever measured, every cosmological conclusion we have ever drawn, all of it has been filtered through 2 billion light-years of below-average density. And we did not know this until 11 years ago. The strangest part is not that this void exists. The strangest part is why it took until 2013 for humanity to realize it was living inside one. How do you know you are standing in a valley if you have never climbed to the top of a mountain? Humanity has been building telescopes for roughly 400 years. From Galileo's first refractor pointed at the moon and the moons of Jupiter to the James Webb Space Telescope, collecting infrared light from galaxies whose photons have been traveling for over 13 billion years, the entire history of observational astronomy is a history of increasingly sophisticated light collection, better mirrors, larger apertures, more sensitive detectors, cameras that can register individual photons, spectrographs that can split the light of a distant galaxy into its component wavelengths and extract from that spectrum information about the galaxy's chemistry, temperature, and motion. All of this apparatus, across 4 centuries of refinement, shares one fundamental characteristic. It detects things that emit or reflect light. It finds photons. It registers brightness. A telescope pointed at an empty void detects nothing, because a cosmic void, by definition, contains too little matter to produce a meaningful amount of light. The instrument cannot tell you the void is there. The void simply does not appear in the data. This is not a technical limitation that better engineering can solve. It is a conceptual one. Astronomy as a discipline was built on the assumption that the universe reveals itself through light, and that assumption, while enormously productive, created a systematic blind spot at cosmic scales. The entire history of observational cosmology is, in a certain sense, a history of confirmation bias operating at the largest possible scale. We looked where things were bright. We catalogued what we found. And from those catalogues, we constructed a picture of the universe that gave enormous prominence to the regions where matter had concentrated, because those were the only regions our instruments could see. Consider the analogy of a detective who only investigates cases with witnesses. Such a detective would build an impressively detailed picture of crimes that happened in public in front of people willing to talk. The case files would be thick, the evidence well documented, the patterns richly analysed. But the majority of crimes, the ones that happened in private without witnesses leaving no one to report them, would be entirely absent from the record. The detective's picture of crime in the city would be systematically skewed toward a specific unrepresentative subset of events. And crucially, the detective would have no way of knowing this from inside the case files alone. Astronomers faced the same problem amplified to cosmic scale. Every galaxy in every catalogue was a witness. Every filament traced across a sky map was a documented event. The voids left no witnesses, generated no data, appeared in no survey. And for most of the history of observational astronomy, there was no method available to even ask the question of what existed in the dark regions between the bright ones. The problem was deeper still. Even the surveys that astronomers did conduct were missing a critical dimension. A galaxy survey in the early 20th century could tell you where a galaxy appeared on the sky, its right ascension and declination, its angular coordinates projected onto the celestial sphere. What it could not tell you was how far away that galaxy was. Two galaxies appearing adjacent to each other in a sky photograph might be separated by 1 billion light-years in actual three-dimensional space, one relatively nearby, one almost at the edge of the observable universe, their apparent proximity purely a consequence of their lying along the same line of sight. Without distance information, you were not mapping the universe. You were mapping its shadow on a flat surface. Imagine standing in a dense forest and looking at the shadow the trees cast on a wall behind you. You would see a two-dimensional silhouette, overlapping shapes, varying densities of darkness, no indication of which trees were near and which were far. Two trees whose shadows overlapped might be 10 meters apart in reality, or 100. The shadow cannot tell you. And from the shadow alone, you could never reconstruct the actual three-dimensional arrangement of the forest. That was the state of galaxy mapping for most of the 20th century. Astronomers had detailed, comprehensive, beautifully observed two-dimensional shadows of a three-dimensional cosmos, and were drawing conclusions about the cosmos as if the shadow were a faithful representation of the thing casting. The tool that finally added the missing dimension was redshift measurement. As the universe expands, the wavelengths of light traveling through it get stretched proportionally to the distance traveled. A galaxy 1 billion light-years away has its light stretched more than a galaxy 500 million light-years away. By measuring precisely how much a galaxy's spectral lines have been shifted toward longer, redder wavelengths, astronomers can calculate how far the light has traveled, and therefore where the galaxy sits in three-dimensional space. The technique had been available in principle since Edwin Hubble used it to establish the expansion of the universe in the 1920s. But applying it systematically to tens of thousands of galaxies across large volumes of space required instruments, computing power, and observing time that did not exist until much later. When the first three-dimensional redshift surveys finally appeared in the late 1970s, the reaction among cosmologists was something between astonishment and institutional vertigo. For decades, theoretical physicists had been building cosmological models on a foundational assumption so elegant and so convenient that it had become invisible, the cosmological principle which states that the universe viewed at sufficiently large scales is homogeneous and isotropic. The same in every place, the same in every direction. This was not merely an aesthetic preference. It was the mathematical bedrock on which every equation describing cosmic expansion, structure formation, and the distribution of matter had been constructed. A universe that obeyed the cosmological principle was tractable. A universe that did not was enormously more complicated. The three-dimensional maps said the universe did not obey it, or at least did not obey it in the way the models assumed. Galaxies were not distributed smoothly through space like grains of rice scattered across a table. They were strung along narrow filaments, concentrated at dense nodes, arranged in thin sheets, and between those structures lay enormous, largely empty volumes that the models had not predicted and that the theory had no ready explanation for. The theorists had spent decades constructing a universe that should look one way, and the data showed it looking dramatically another. It was, to borrow the outline's analogy, rather like a navigator confidently following a map, only to discover upon finally reaching a hilltop that the map had been printed upside down. The roads were real, the destinations existed, but the relationship between them was the reverse of everything the navigator had assumed. This was the moment the cosmological principle stopped being an invisible assumption and became a testable claim, and one that was beginning to show cracks. The principle was not immediately abandoned. It remained, and still remains, an enormously useful approximation at scales large enough. But the three-dimensional surveys had introduced a new question into the heart of cosmological science. How large is large enough? At what scale does the universe actually become smooth? And what lives in the enormous volumes between the bright structures that the surveys were beginning to reveal? Those questions have been getting harder to dismiss with every subsequent decade of observation. The KBC void, 2 billion light-years across and 20% below the cosmic average in matter density, surrounds us on all sides. It is not a small wrinkle in an otherwise uniform fabric. It is a dominant feature of the local cosmos, and it is centered on us. The cosmological principle says our position should not be special. The data suggest it might be. When the first three-dimensional maps were printed, the most striking feature was not the galaxies. It was the enormous black regions in between, and nobody had a theory that could explain them. If empty does not mean nothing is there, then what does it mean? There is a word that causes problems the moment it enters a conversation about cosmic voids, and that word is empty. The problem is not that the word is inaccurate. It is that the word carries a meaning in everyday language that is far more absolute than what physicists intend when they use it. When someone tells you a room is empty, they mean no furniture, no people, nothing of consequence. When a glass is empty, it contains no liquid worth mentioning. Emptiness in the human vocabulary is a binary condition. Either something is there or it is not. Cosmic voids do not work that way. A cosmic void is not a hole punched through the fabric of space where matter has been surgically removed. It is not a region where some catastrophic event swept the area clean, leaving behind a perfect vacuum stretching across hundreds of millions of light years. If you could somehow transport yourself to the geometric center of the KBC void and look around in every direction with the most powerful telescope ever conceived, you would find galaxies. Not many, far fewer than you would find in a typical region of the cosmos, but they would be there. Stars would be burning inside them. Gas clouds would be drifting between them. Dark matter, the invisible gravitational scaffolding that permeates the entire universe, would fill the volume in a thin, ghostly web too diffuse to collapse into anything new, but present nonetheless. What makes a cosmic void is not the absolute absence of matter. It is a significant deficit of matter relative to the cosmic average. Astronomers calculate a mean density for the observable universe, a number representing how much matter you would expect to find on average in any given volume of space if you sampled the cosmos randomly across billions of light years. Void regions contain somewhere between 10 and 30% of what that average predicts. Not zero, not close to zero by the standards of a laboratory vacuum, but far enough below the mean to produce consequences that reshape the behavior of everything inside. Think about what it means to call a place sparsely populated. The Sahara Desert is not uninhabited. Communities live there, roads cross it, life has adapted to its conditions over millennia. But compare the population density of the Sahara to that of the Red River Delta in Vietnam, one of the most densely settled agricultural plains in Asia, and you are comparing two realities so different that the same category of inhabited land barely covers both. The desert is not empty in an absolute sense. It is underdense relative to what the same area of land might contain under different conditions. The distinction matters because it determines what is possible there, what kinds of communities can form, what resources are available, what future is on offer for anything trying to survive in that environment. Cosmic voids operate on precisely this logic, scaled up by factors that make the Sahara to Delta comparison seem trivial. The interior of a void is not a dead zone. It is an environment where the rules of cosmic development play out very differently than they do in the dense filaments and cluster nodes of the cosmic web, because the raw material gravity's raw material matter itself is so thinly spread that the processes which build structure elsewhere simply cannot operate with the same effectiveness. And that interior has a structure of its own. Voids are not uniform underdensities. They have a characteristic profile that astronomers have mapped through statistical techniques applied to thousands of examples. At the geometric center of a void, the matter density reaches its minimum, the deepest part of the deficit. Moving outward from that center density gradually increases slowly at first, then more steeply as you approach the void's boundary. At the edge, the density rises above the cosmic average, sometimes significantly so. forming what researchers call the compensation wall. This ridge of above-average density is not an accident. It is the direct consequence of the void's evolution. Over billions of years, the void has been pushing matter outward, sweeping it toward the boundaries where it piles up against the surrounding structures like snow, accumulating at the edge of a plow's path. Those surrounding structures are the rest of the cosmic web, and understanding a void requires understanding what it is embedded within. The large-scale structure of the universe is organized into 4 distinct components. First, there are nodes, the densest intersections where multiple filaments converge, hosting massive galaxy clusters packed with hundreds or thousands of galaxies, superheated gas glowing at temperatures of hundreds of millions of degrees, and supermassive black holes at their centers. Second, filaments, the elongated threads connecting these nodes, channeling matter across hundreds of millions of light-years like cosmic supply lines. Third, walls, also called sheets, broad, flat concentrations of galaxies forming where filaments meet along 2-dimensional surfaces, thinner and more diffuse than filaments, but spanning truly enormous distances. And fourth, voids, the interiors of the bubbles that all of these structures surround. The cosmic web is often described with the analogy of a sponge, and the analogy is apt in one important respect. In a sponge, what strikes you first is not the solid material forming the walls and channels, but the open space filling the sponge. Pores. The voids are the pores. They are not a secondary feature of the web, tucked away in the background, while the filaments and clusters do the important work. They are the dominant spatial feature of the entire structure, occupying, as established earlier, somewhere between 80 and 90% of the observable universe's volume. The 4 components of the cosmic web are real, but 3 of them share a minority of the total space. The 4th component, the voids, owns the rest. And crucially, the voids are not sitting still. A cosmic void is not a static feature frozen into the cosmic landscape at some point in the past, waiting passively for astronomers to notice it. It is an active, evolving, self-reinforcing process. Matter drains from the void interior toward the surrounding structures, driven by the gravitational pull of the denser regions beyond the void's edge. As matter leaves, the interior becomes less dense. As the interior becomes less dense, its gravitational influence weakens further. As its gravitational influence weakens, less resistance remains to oppose the expansion of space driven by dark energy. The void expands. As it expands, the same remaining matter now occupies a larger volume, making the density lower still. And so the cycle continues, each step accelerating the next with no natural mechanism to reverse or even slow the progression. This is the specific environment where dark energy, the mysterious pressure driving the accelerating expansion of the universe, achieves its most complete and uncontested dominance. In galaxy clusters, gravity is powerful enough to hold structures together against dark energy's outward push, and has been doing so for billions of years. In filaments, gravity still exerts meaningful resistance. But inside a void where matter is so sparse that gravitational attraction across the void's interior is negligible, dark energy encounters almost no opposition. It expands the void without a fight. The void grows larger. The void grows emptier. And nothing in the current laws of physics as we understand them can reverse that trajectory. A void is making itself emptier every day, and no force in the universe can stop it. But that is not yet the most unsettling part. If you knew that the house you live in is not a normal part of the city, how would that change the way you understand the city itself? Astronomy has always been a discipline practiced from a fixed address. We observe from Earth, which orbits the Sun, which sits roughly 26,000 light-years from the center of the Milky Way, which is part of the Local Group, a collection of roughly 80 galaxies gravitationally bound together, across a volume of about 10 million light-years. The Local Group is itself a member of the Laniakea supercluster, a vast gravitational basin containing approximately 100,000 galaxies spread across 520 million light-years, all of them flowing together toward a common gravitational center astronomers call the Great Attractor. That is an impressive address by almost any measure. Laniakea is one of the largest coherent gravitational structures that has been mapped in the observable universe. When you hear those numbers, 100,000 galaxies, 520 million light-years, they carry a weight that feels definitive as though belonging to such a structure places you somewhere consequential in the cosmos. Then you set Laniakea inside the KBC void, and the perspective inverts completely. The KBC void spans approximately 2 billion light-years in diameter. Laniakea, at 520 million light-years across, fits inside that diameter roughly 4 times over in any single direction. The entire supercluster, with all its galaxy groups, its dozens of major clusters, its 100,000 galaxies, its billions upon billions of individual stars, occupies a volume that is dwarfed by the void, containing it the way a backyard swimming pool is dwarfed by the Pacific Ocean. If the KBC void were the Pacific Ocean in this comparison, Laniakea would be a family-sized pool floating somewhere in the middle of it. The Milky Way nested inside the local group nested inside Laniakea would be something smaller, still a coffee cup floating in the pool. This is not a poetic exaggeration. It is the proportional reality of our location in the universe, and it has consequences that extend far beyond questions of cosmic architecture. The central issue is this: we do not observe the universe from a neutral representative vantage point. Every observation we make, every measurement we take, every data set we compile about the cosmos beyond our immediate neighborhood passes through the particular environment in which we happen to be located. And that environment, as we have established, is a region of space where the density of matter runs roughly 20% below the cosmic average, extending in every direction for approximately 1 billion light-years. The universe that our instruments see is not the universe as it appears from a statistically typical location. It is the universe as it appears from inside an unusually large underdensity, filtered in every direction through 2 billion light-years of below-average matter content. The consequences of this filtering are not obvious, and they were not obvious to the generations of astronomers who built the field without knowing they were inside the void. To understand why it matters, consider a simple analogy. Imagine you are asked to measure the average temperature of a large city, and you place your thermometer on the exterior wall of a building that happens to have its air conditioning unit venting directly onto the sensor. Your thermometer would give you an accurate reading of the temperature at that specific location. The measurement would be precise, reproducible, and technically correct. But the conclusion you drew from it, that the city as a whole is at that temperature, would be systematically wrong, biased by the specific atypical conditions of your measurement location. You would not know this unless you also had measurements from other locations to compare against, or unless someone pointed out that the thermometer was next to the air conditioning vent. Our cosmological measurements face an analogous problem. The KBC void creates local conditions that differ in measurable ways from the cosmic average. Inside, the void matter is sparser, gravitational pull is weaker, and dark energy faces less opposition, which means space within the void expands slightly faster than it does in regions of average density. Galaxies inside the void experience a net gravitational pull directed outward toward the denser walls and filaments beyond the void's edge, which adds a systematic outward velocity to their motion on top of whatever the underlying cosmic expansion would produce. When we measure the recession velocities of galaxies in our cosmic neighborhood and use those velocities to calculate how fast the universe is expanding, we are measuring the expansion of the universe, plus this additional outward push from the void. We cannot easily separate the two contributions from inside the void itself. This brings us to the measurement that has haunted cosmology for more than a decade, a disagreement so persistent and so technically robust that it has earned its own name, the Hubble tension. The Hubble constant is the number that quantifies the expansion rate of the universe, the speed at which space stretches between any 2 points separated by a standard cosmological distance. 2 independent, highly refined methods of measuring this number have been applied by different teams using different instruments, different calibration techniques, and different portions of cosmic history. Both methods are extraordinarily precise by the standards of modern science. Both have been checked, cross-checked, and scrutinized for sources of error for years. They disagree by approximately 9%. One method, which looks at the cosmic microwave background radiation, the ancient light released 380,000 years after the Big Bang, gives a value of approximately 67 kilometers per second per megaparsec. The other method, which measures the expansion rate directly using nearby supernovae and variable stars as cosmic distance markers, gives approximately 73 kilometers per second per megaparsec. 9% sounds modest. At the precision levels these measurements have achieved, it represents a statistical discrepancy of 5 sigma, the threshold that physicists use to declare the discovery of a new phenomenon. The probability of this disagreement arising by chance is less than 1 in a million. Both measurements are almost certainly correct descriptions of what they are actually measuring. The question is whether they are measuring the same thing. The KBC void suggests they may not be. The cosmic microwave background measurement samples the expansion history of the entire universe averaged across the full, observable volume, independent of our local position. It is a global measurement. The local supernova and variable star measurements probe the expansion rate within our cosmic neighborhood, which is specifically the interior of the KBC void. If the void is causing nearby galaxies to move outward faster than the cosmic average expansion rate alone would predict, then the local measurement would record a higher apparent expansion rate than the global one. Not because the universe is actually expanding faster in our region, but because we are adding void-driven outflow on top of the expansion and interpreting the total as expansion alone. The thermometer is next to the air conditioning vent, and we have been recording the reading without checking where we placed the sensor. This does not mean everything cosmologists have measured is wrong. The measurements are real, the data are solid, but data always requires interpretation, and interpretation always requires assumptions about the conditions under which the data were collected. The assumption that our local cosmic environment is representative of the universe at large may be the assumption that is failing us. If our position inside the KBC void systematically inflates our local measurement of the expansion rate, then the Hubble tension is not evidence of broken physics. It is evidence of an unexamined premise about where we are standing. How much of what we think we know about the universe is actually knowledge about our specific atypical corner of it? That question has no clean answer yet, but it is no longer a philosophical speculation. It is an active research problem sitting at the center of the most significant unresolved debate in modern cosmology. There is a number that 2 groups of the world's best scientists have measured and remeasured for decades, and they have never agreed. The reason may not be that either group is wrong. It may be that both are standing in different places in the universe. If the 2 most precise measuring instruments in the world give different results, which one do you throw away? Every field of science has its arguments. Disagreements over interpretation, debates about methodology, competing models that make slightly different predictions, and wait for better data to settle the question. These are the ordinary frictions of scientific progress, productive tensions that eventually resolve into clearer understanding. They are not crises. They are the mechanism by which science advances. The Hubble tension is not one of those ordinary disagreements. It is something qualitatively different, a conflict so precisely quantified, so thoroughly examined, and so stubbornly persistent that it has forced cosmologists to confront the possibility that something fundamental is missing from their picture of the universe. Not a missing detail, a missing premise. To understand why the tension is so troubling, start with what the Hubble constant actually represents. Named after Edwin Hubble, who first demonstrated in 1929 that distant galaxies are receding from us at velocities proportional to their distance, the Hubble constant quantifies the expansion rate of the universe. It tells you that for every additional megaparsec of distance between 2 points in space, 1 megaparsec being roughly 3.26 million light-years, the space between them is stretching at a certain speed, measured in kilometers per second. This rate governs the age of the universe, the distances to remote objects, the balance between matter and dark energy, and ultimately the entire future trajectory of cosmic evolution. It is not a peripheral number. It is the heartbeat of the cosmos, and getting it right is one of the central ambitions of modern cosmology. 2 methods have been developed to measure it. They are independent in the most meaningful sense of the word. They use entirely different physical phenomena, probe entirely different epochs of cosmic history, and were developed by different research communities using different instruments, on different telescopes, over different decades. If physics is consistent with itself as it should be, they should agree. The first method looks backward to the earliest observable moment in cosmic history. The cosmic microwave background is the relic radiation released approximately 380,000 years after the Big Bang. when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, photons were trapped in a dense plasma unable to travel freely. When neutral atoms formed, the photons were released, and they have been traveling through the expanding universe ever since. Satellites, including the Planck spacecraft, have mapped this radiation across the entire sky with extraordinary precision, measuring the minute temperature variations that encode the density fluctuations of the early universe. By feeding this map into the standard cosmological model, physicists can calculate what the expansion rate must be today, given the conditions that existed 380,000 years after the Big Bang. The answer this method produces is approximately 67 kilometers per second per megaparsec. The second method looks at the nearby universe, the cosmos, as it exists in our own cosmic epoch, measurable in real time. It relies on objects whose intrinsic brightness is known with high confidence, allowing astronomers to calculate their distance by comparing how bright they appear to how bright they actually are. The most important of these so-called standard candles are Type Ia supernovae, explosions of white dwarf stars that occur through a well-understood physical mechanism and reach a consistent peak luminosity and Cepheid variable. Stars which pulse with a period directly related to their intrinsic brightness. Chains of these calibrated distance markers, carefully cross-referenced and refined over decades, allow researchers to measure the recession velocities of galaxies at known distances and extract the local expansion rate directly. The SH0ES collaboration, led by Adam Rees, and among the most careful and extensively reviewed efforts in modern astrophysics, consistently measures a value of approximately 73 kilometers per second per megaparsec. 67 versus 73, a difference of roughly 9%, stated that way 9% sounds like something that better measurements might resolve a remaining calibration, imprecision, a systematic error lurking in one of the methods, a correction that future data will supply. The history of science is full of measurements that converged once the techniques matured. Surely this is one of those cases. Except the error bars on both measurements have been shrinking for years, and the central values have not moved toward each other. They have stayed apart, and as the precision has improved, the statistical significance of the gap has grown. The disagreement currently stands at approximately 5 sigma. In the language of statistics, 5 sigma means that if both measurements were drawing from the same underlying true value, the probability of them differing by this amount through random chance alone is less than 1 in a million. In particle physics, a 5 sigma result is the formal threshold for announcing a genuine discovery. In cosmology, a 5 sigma disagreement between two established measurement methods is not a calibration problem. It is a signal that something is wrong with the framework connecting them. The field has not been passive. Proposed solutions have accumulated over more than a decade, each examined carefully and ultimately found insufficient. Early dark energy, a hypothetical burst of additional energy density in the first few 100,000 years of cosmic history, could in principle shift the predicted expansion rate upward, but models incorporating it create new tensions with thirst. Other observations that are equally difficult to resolve. Dynamical dark energy, which changes in strength over time, rather than remaining the constant assumed in the standard model, has been explored extensively without producing a clean resolution. Modifications to the theory of gravity at cosmological scales have been proposed and constrained. Systematic errors in the Cepheid calibration chain have been scrutinized from every angle, including by the James Webb Space Telescope, which confirmed the ground-based measurements rather than overturning them. None of these approaches has closed the gap. The tension persists. What the KBC void offers is a fundamentally different kind of explanation, one that requires no new particles, no modifications to gravity, no exotic fields, and no revision of fundamental physics. It requires only the recognition that our measurement location is not cosmologically neutral. The logic is straightforward. The cosmic microwave background measurement is a global probe. It samples the expansion history of the entire observable universe, integrating over billions of light-years of cosmic volume across billions of years of cosmic time. The local underdensity of the KBC void is a small feature in that global picture, too small and too nearby to significantly bias a measurement of the full universe's expansion history. The approximately 67 kilometers per second per megaparsec result reflects to a good approximation the true average expansion rate of the cosmos. The supernova and Cepheid measurements are local probes. They sample the expansion rate of the universe within our immediate cosmic neighborhood, which means within the KBC void. And inside the void, as established in the previous section, galaxies are not only receding due to cosmic expansion, they are also being pushed outward by the gravitational deficit of the void itself. Matter is sparse in the interior. The dense walls and filaments beyond the void's edge pull everything inside outward, adding a systematic bulk velocity on top of whatever the underlying expansion would produce. When local measurements capture the recession velocity of a nearby galaxy and attribute the entire velocity to cosmic expansion, they are counting the void's outflow as expansion. The measured rate comes out higher than the true global rate, not because the universe is actually expanding faster locally, but because our instruments cannot distinguish the two contributions without knowing we are inside an underdensity. The magnitude of the predicted bias from a void of the KBC's dimensions and depth is consistent within the uncertainties of current modelling, with the observed gap between the two measurements. A void, approximately 2 billion light-years across, with a matter density deficit of roughly 20%, produces an outflow that could boost the apparent local Hubble constant by several kilometers per second per megaparsec, enough to account for a meaningful fraction of the discrepancy, and potentially all of it depending on the assumed void profile. This is not a guarantee. The void hypothesis for the Hubble tension is a serious scientific proposal, not a proven solution, and the research community continues to test it against additional data. But it carries a particular kind of intellectual weight that the exotic physics proposals lack. It does not require anything new to be true about the universe. It requires only something true about our location to be properly accounted for. We have been measuring the expansion rate of the universe while standing inside an unusual outflow region without correcting for the outflow because we did not know we were inside it. The universe has not been hiding its true expansion rate from us behind some exotic new force. It has been giving us accurate numbers all along. We simply forgot to check where we placed the thermometer. If the KBC void is the true cause of the Hubble tension, then the universe is not more mysterious than we thought. It has simply been laughing at us for forgetting to check where we were standing. What would happen if nothing never truly existed, even before the universe was born? There is a question that sounds like philosophy, but turns out to be physics, and it goes like this. Before the universe contained anything, before the first atom, before the first photon, before the forces of nature had settled into the forms we recognize today, was there ever a moment of true, absolute, perfect nothingness? The answer, as best as modern physics can determine, is no. There was not. And that fact, strange as it sounds, is where every cosmic void in the observable universe, including the 2 billion light-year emptiness surrounding the Milky Way, ultimately begins. To understand why, you need to sit with a concept that quantum mechanics established over the course of the 20th century, and that has been confirmed by experiment after experiment to a precision that rivals any result in science. The quantum vacuum is not empty. The word vacuum in everyday usage means the absence of matter, a space scrubbed clean of particles, gases, and anything that might obstruct it. In classical physics, a perfect vacuum is exactly that, a region containing nothing where all physical quantities sit at zero and remain there. This is the intuition most people carry about empty space, and it is comprehensively wrong at the quantum level. In quantum mechanics, every field that permeates the universe, the electromagnetic field, the fields associated with subatomic particles, the Higgs field that gives matter its mass, is subject to an irreducible, inescapable fluctuation. Even in its lowest possible energy state, a quantum field does not sit still. It trembles. It oscillates around its ground state in a manner that cannot be suppressed by cooling the environment, removing all particles, or isolating the region from external influence. These oscillations are not the result of anything happening to the field. They are a consequence of the uncertainty principle, which forbids any physical quantity from simultaneously having a precisely defined value and a precisely defined rate of change. The field must fluctuate, because a field that was perfectly still and perfectly at rest would violate the foundational mathematics of the theory. The practical consequence of this is that the vacuum of space seethes with activity at scales far below anything detectable by direct observation. Virtual particle pairs appear and annihilate on timescales so brief that they never accumulate into anything stable. Energy density fluctuates from point to point across distances smaller than an atomic nucleus. The electromagnetic field jitters in ways that produce measurable forces between nearby conducting surfaces, a phenomenon called the Casimir effect that has been verified in laboratories to remarkable precision. Empty space, it turns out, is one of the most energetically active environments in nature. It just operates on scales so fantastically small that nothing in the macroscopic world can resolve the activity. Under ordinary circumstances, this quantum activity in the vacuum is cosmologically irrelevant. The fluctuations occur at scales trillions of times smaller than any structure that gravity could act on. They average out over any volume larger than subatomic dimensions, producing no net effect on the distribution of matter or energy at scales relevant to stars, galaxies, or anything larger. If the universe had simply expanded at a moderate, steady rate from its beginning, these quantum tremors in the vacuum would have remained permanently at subatomic scales, and the large-scale structure of the cosmos might have been something far smoother and more uniform than what we observe. But the universe did not expand at a moderate, steady rate from its beginning. In the earliest fraction of its first second, an interval so short that it makes a billionth of a second look like a geological epoch. By comparison, the universe underwent a period of expansion so violent and so rapid that it has earned its own name, inflation. During this epoch, the universe expanded by a factor of at least 10 to the power of 26, possibly much more. Space itself stretched at a rate that vastly exceeded the speed of light. Not because anything moved through space faster than light, but because space itself was expanding faster than light could cross it. A region the size of a subatomic particle ballooned into a volume larger than what would eventually become the observable universe, in an interval measured in units of 10 to the negative 36 seconds. What inflation did to the quantum fluctuations in the vacuum was, by any reasonable measure, the most consequential thing that has ever happened in the history of the cosmos. It stretched them. It took oscillations operating at scales smaller than a proton and expanded them along with everything else to macroscopic dimensions. A fluctuation that represented a tiny excess of energy density in a volume smaller than an electron was inflated to a scale that would eventually encompass hundreds of millions of light years. A fluctuation representing a tiny deficit of energy density underwent the same treatment. By the time inflation ended, these stretched fluctuations were imprinted across the fabric of space as permanent frozen variations in energy density, too large to continue oscillating, too diffuse to collapse back into the subatomic realm from which they came. The image that best captures this process is close to the following. Imagine photographing the surface of human skin at extreme magnification, close enough to resolve individual pores, the microscopic texture of the epidermis, the fine grain of the cells beneath. At that scale, the surface is complex and varied, full of hills and valleys that are invisible to the naked eye. Now imagine that surface being inflated like a balloon to a size where each of those microscopic features has grown to the scale of a mountain range. The pores have become valleys the size of the Grand Canyon. The ridges between them have become continental divides. The microscopic texture of the skin, originally invisible and cosmologically insignificant, has become the large-scale topography of a planet. Inflation performed this operation on the quantum texture of the early universe, and the resulting topography became the blueprint from which all cosmic structure would eventually be built. The regions where quantum fluctuations had produced a slight excess of energy density became, over billions of years, the seeds of galaxy clusters and the dense filaments of the cosmic web. The regions where quantum fluctuations had produced a slight deficit became the seeds of cosmic voids. The numbers involved in this inheritance are staggering in both directions. The initial density variations that inflation left behind were extraordinarily small deviations of roughly 1 part in 100,000 from the mean energy density. At the moment inflation ended, the universe was almost perfectly uniform. An observer with instruments sensitive enough to detect 1 part in 100,000 variations would have noticed the fluctuations. An observer with slightly less precise instruments would have seen nothing but smooth, featureless, evenly distributed energy, stretching in all directions. The seeds of the cosmic web were there, but they were invisible, buried in a universe that looked to any reasonable approximation like a place where nothing interesting would ever happen. 14 billion years of gravity disagrees with that assessment, but the starting point remains the KBC void, the 2 billion light-year underdensity within which the Milky Way and the entire Laniakea supercluster are embedded, began as a quantum fluctuation smaller than a proton occurring, during an interval shorter than any unit of time that carries physical meaning in a universe that did not yet contain a single atom. The largest confirmed structure of emptiness in the observable cosmos traces its existence to a random downward tremor in a quantum field that no instrument will ever directly observe. Modern cosmology has in effect discovered that the largest structure in the history of the universe was decided by pure luck at the subatomic scale. If that does not keep theoretical physicists awake at night, nothing will. But the quantum seed is only the starting point. Something had to transform a tiny downward fluctuation into a 2 billion light-year emptiness. And that something is the most patient force in the universe. If gravity only pulls matter together, why does it create regions that grow progressively emptier over time? Gravity has a reputation problem. In the popular imagination, it is the force of attraction, the thing that holds the solar system together, keeps feet on the ground, pulls apples from trees, and by extension, assembles matter into stars, galaxies, and the great structures of the cosmos. This reputation is earned. Gravity is over cosmic scales the primary architect of everything visible in the universe. But the reputation is incomplete, in a way that matters enormously for understanding how cosmic voids came to exist and why they continue to grow. Gravity does not only build, it excavates. The same force that assembles dense structures simultaneously hollows out the regions surrounding them, and it does so not as a side effect or a secondary consequence, but as an intrinsic part of its operation. You cannot have one without the other. Every filament of galaxies that gravity has constructed over the past 14 billion years has been built at the direct expense of the surrounding regions which gravity systematically drained to supply the raw material. The structure and the emptiness are not separate products of separate processes. They are two aspects of a single unified dynamic. The mechanism is called gravitational instability, and its logic is brutally simple. Consider a universe in which matter is distributed almost but not quite uniformly, with tiny variations in density scattered throughout exactly the kind of variations that inflation imprinted on the early cosmos. In any region where the local density is even slightly above the mean, gravity is slightly stronger than average. That marginally stronger gravitational pull attracts matter from the surrounding volume. The region becomes denser. As it becomes denser, its gravitational pull increases further. More matter is drawn in from a wider surrounding area. The density contrast grows. The process accelerates. Over billions of years, what began as a 1 part in 100,000 excess becomes a galaxy group, then a galaxy cluster, then the dense node of a cosmic filament containing millions of stars. Meanwhile, the regions that lost matter to build those structures are doing the opposite. A region that was initially slightly below the mean density has a slightly weaker gravitational pull than its neighbors. The overdense regions on its boundaries pull matter away from it rather than toward it. The underdense region loses mass. As it loses mass, its gravitational pull weakens further. As its gravitational pull weakens, it becomes even less able to retain the matter that remains. The neighboring overdense regions continue drawing matter outward. The underdense region empties further. Over the same billions of years, what began as a 1 part in 100,000 deficit evolves into a void, a region of space that now contains only a fraction of the matter a typical volume would hold. The analogy that captures this dynamic most cleanly comes not from physics but from economics. Consider the distribution of population across a country that contains both large cities and rural areas. A large city offers employment infrastructure and opportunities that small towns cannot match. People move toward the city. As the city's population grows, it generates more economic activity, more services, more reasons to relocate there, attracting still more people from still wider distances. The rural areas, meanwhile, lose their young and their ambitious to the city. As their populations decline, the economic case for maintaining services in those areas weakens. Shops close. Transport links deteriorate. The remaining residents have fewer reasons to stay and fewer resources to develop new ones. the rural areas empty further. Nobody decided this would happen. No central authority directed the process. It is the natural dynamics of a system in which resources flow toward concentration and away from dispersal, and it is irreversible without an external force powerful enough to counteract the underlying gradient. Gravitational instability operates on precisely this logic across cosmic scales and cosmic timescales, with patience that makes the longest human institution look ephemeral. The timescales involved stretch across hundreds of millions and billions of years. The density contrasts that inflation produced, those 1 part in 100,000 variations, required several 100 million years just to become visible as distinct structures in galaxy surveys. The first stars formed, lived their brief, violent lives and died. The first galaxies assembled from the merger of smaller protogalactic clouds. The first galaxy groups formed along the early filaments. And through all of this, the underdense regions were simultaneously draining their matter, flowing outward along the density gradients of the gravitational field toward the growing concentrations. By the time the universe was several billion years old, the small initial fluctuations had been amplified into a recognizable cosmic web, the same web whose structure was described in the previous section, with its dense nodes and filaments, and thin walls, all of them separated by voids that were already hundreds of millions of light-years across. The process that began with 1 part in 100,000 quantum noise had, through nothing more exotic than ordinary gravity, operating across ordinary time, produced structures that no human mind had anticipated, before the redshift surveys of the late 1970s revealed them. The modern tool for verifying this understanding is the cosmological simulation. Supercomputers running purpose-built codes take as their input the initial conditions of the early universe derived from precise measurements of the cosmic microwave background and run the laws of physics forward across billions of simulated years, tracking the motion of billions of simulated particles representing dark matter, ordinary matter, and energy. The output of these simulations, when visualized, is almost indistinguishable from what actual galaxy surveys. Observe filaments threading across the virtual sky, dense nodes glowing at their intersections, thin walls of galaxies spanning hundreds of millions of light-years, and between them voids. The simulations produce voids naturally, without requiring them to be inserted by hand. Gravitational instability alone, operating on quantum-seeded initial conditions, generates them. This agreement between simulation and observation is one of the great intellectual achievements of late 20th and early 21st century science. It means that the architecture of the universe, the specific arrangement of every filament and void in the observable cosmos, is not arbitrary. It is the deterministic consequence of initial conditions that were themselves set by inflation amplifying quantum fluctuations. Given the specific pattern of temperature variations in the cosmic microwave background, one can in principle predict where the cosmic web should be, and the prediction matches what galaxy surveys find. But the simulations have a boundary beyond which their explanatory power begins to strain. When the voids being modelled are small to medium in scale, up to a few 100 million light-years across, well within the range that standard theory comfortably predicts, the match between simulation and observation is excellent. When the voids approach the dimensions of the KBC void, 2 billion light-years across, 20% below the cosmic average centered on our own position, the simulations begin to struggle. Generating a structure of that specific size and that specific depth within the standard cosmological framework requires initial conditions that the model predicts should occur only rarely. Some analyses have placed the statistical probability of finding a void this extreme at several standard deviations from the expected distribution deep into the tail of the probability curve, in territory that the model says should almost never occur. This does not mean the model is wrong. Rare events happen, and a single anomalous observation cannot overturn a framework that successfully explains thousands of other observations. But it does raise a question that has no clean answer yet. Either the KBC void is a genuine statistical outlier, the universe's equivalent of a 1 in a million roll of the cosmic dice, or the initial conditions that gave rise to it were somehow more extreme than the standard model predicts they should have been, or the model is missing a piece of physics that would make such structures less surprising than current theory suggests. The simulations have confirmed the mechanism. Gravity operating on quantum seeds across billions of years produces the cosmic web. What they have not yet fully explained is why our particular corner of that web contains an emptiness this large and this deep. Gravity spent 14 billion years sculpting the universe into the shape it holds today. But there is another force, one whose fundamental nature we do not yet understand, that is slowly dismantling everything gravity built. If 68% of the universe's energy comes from something science does not understand, what does that tell you about what science actually knows? There is a number that sits at the center of modern cosmology, like the locked room that everyone can measure from the outside, but nobody has managed to open. That number is 68%. It represents the share of the total energy content of the observable universe, attributed to dark energy, the component responsible for the accelerating expansion of space. The other 32% is split between ordinary matter, the kind made of atoms, and detectable by every instrument humanity has ever built, and dark matter, the invisible gravitational scaffolding, whose existence is inferred from its effects on the things we can see. Ordinary matter. Every star, every planet, every nebula, every galaxy, every atom of hydrogen and carbon and iron that has ever participated in any physical process, we have directly observed constitutes roughly 5% of the total energy. Budget. Dark energy constitutes 68%, and science does not know what it is. This is worth sitting with for a moment, because the temptation when encountering this fact is to reach immediately for reassurance, to note that science has made great progress, that the models work remarkably well, that the existence of dark energy has been confirmed through multiple, independent lines of evidence. All of that is true, but the reassurance should not be allowed to obscure what the number actually says. The dominant component of the universe, the ingredient that determines the long-term fate of every structure in the cosmos, the force that is currently winning its contest with gravity across the vast majority of cosmic volume, that the component is at the level of fundamental physical understanding, a mystery. We know it exists. We know what it does. We have no confirmed theory of what it is. The discovery of dark energy arrived in 1998 through observations of Type Ia supernovae at high redshift. Two independent teams, the Supernova Cosmology Project and the High Z Supernova Search Team, found that distant supernovae appeared fainter than expected for a universe whose expansion was slowing down under the influence of gravity, as all models at the time assumed it should be. The only explanation consistent with the data was that the expansion of the universe was not slowing. It was accelerating. Something was pushing space apart at an increasing rate, overpowering the collective gravitational pull of all the matter in the cosmos across large scales. That something received the placeholder name dark energy, and the discovery earned its principal investigators the Nobel Prize in Physics in 2011. Two serious theoretical candidates have been proposed for dark energy's identity, and they make predictions that are in principle distinguishable through observation. The first candidate is the cosmological constant, a term that Einstein originally introduced into his equations of general relativity and later withdrew, but which the supernova data effectively reinstated. The cosmological constant represents a fixed, uniform energy density woven into the fabric of spacetime itself, independent of position and time. It does not dilute as the universe expands, does not change as cosmic history unfolds, and exerts the same outward pressure everywhere and always. It is, in the most literal sense, the energy of empty space, a baseline level of energy that the vacuum of the universe possesses simply by existing. The second candidate is a dynamical field, sometimes called quintessence, whose energy density and pressure can vary across both space and time. Unlike the cosmological constant, a dynamical dark energy field is not fixed. It evolves as the universe ages, potentially strengthening or weakening as cosmic conditions change. It might be stronger in some regions of space than others, depending on local conditions. Its equation of state, the mathematical relationship between its energy density and its pressure, might drift over cosmic timescales, tracing a trajectory through parameter space that a cosmological constant would never follow. Distinguishing between these two candidates is one of the central observational challenges of 21st century cosmology. And this is where cosmic voids enter the picture, not merely as subjects of study, but as instruments of measurement. arguably the most precisely calibrated instruments available for probing dark energy's behavior. The reason comes back to the competitive dynamics described in the previous section. In galaxy clusters and the dense nodes of the cosmic web, dark energy and gravity are engaged in an ongoing contest. Gravity pulls matter together, dark energy pushes space apart. In the densest environments, gravity wins decisively. Clusters hold together, galaxies merge, structure continues to grow despite the outward push of dark energy. The two forces are both present, both significant, and their interplay creates a complicated signal that is difficult to disentangle cleanly. Trying to measure dark energy's properties from inside a galaxy cluster is like trying to measure the background noise level in a room while a concert is playing. The signal is real, but the contamination from other sources makes precision difficult. Inside a cosmic void, the concert stops. Matter is so sparse that gravitational attraction across the void's interior is negligible by cosmic standards. The dense walls and filaments lie beyond the void's edge, too distant to dominate the local dynamics. Dark energy faces no meaningful gravitational competition within the void's volume. It operates to an approximation unavailable anywhere else in the observable universe alone. The expansion of the void is therefore a nearly pure measurement of dark energy's behavior, stripped of the gravitational noise that contaminates measurements made in denser environments. The shape of voids carries particularly powerful diagnostic information. If dark energy is truly a cosmological constant, identical in strength everywhere and at all times, then voids should expand at the same rate in every direction, preserving their roughly spherical geometry as they grow. A void that began as an approximately round underdensity should remain approximately round because there is no physical reason for dark energy if it is uniform to push harder in one direction than another. If dark energy is instead a dynamical field that varies across space or evolves over time, the situation changes. A field with spatial variations would exert different pressures in different directions within a void, causing it to expand faster along some axes than others and distorting its shape away from spherical. A field that grows stronger over cosmic time would cause older voids, those that formed earlier in cosmic history, and have been expanding longer, to be more distorted than younger ones, leaving a measurable signature in the statistical distribution of void shapes at different redshifts. Current observations, while precise by the standards of a field that has existed for only a few decades, still carry uncertainties large enough to permit a range of dark energy models. The data accumulated through surveys, including the Sloan Digital Sky Survey and the Dark Energy Survey, are consistent with the cosmological constant hypothesis. Dark energy appears to have been approximately uniform and stable over the past several billion years, the period for which high-quality void-shape measurements are available. But the error bars remain wide enough that subtle variations at the level that many theoretical models predict cannot yet be ruled out. The cosmological constant is the simplest hypothesis consistent with current data. It is not the only one. This is where missions currently under development and recently launched become critical. The Euclid Space Telescope, a European Space Agency mission that began science operations in 2023, is designed to map the shapes and positions of hundreds of millions of galaxies across a significant fraction of the sky, extending back to a redshift of 2, looking roughly 10 billion years into the past. From this dataset, researchers will extract a catalogue of cosmic voids numbering in the thousands at many different distances and correspondingly different epochs of cosmic history. Each void in that catalogue is an independent measurement of dark energy's behaviour at a specific moment in time and a specific location in space. Together, they form a multidimensional portrait of how dark energy has acted across the universe's history. The Vera Rubin Observatory, a ground-based facility in Chile, now entering its operational phase, will conduct the Legacy Survey of Space and Time, a 10-year photometric survey covering an enormous area of the southern sky to extraordinary depth. It will produce void catalogues, complementary to Euclid's, extending the statistical power of void-based dark energy measurements and enabling cross-checks between independent datasets that will be essential for controlling systematic errors. These surveys will over the coming decade either confirm that dark energy is the featureless cosmological constant that the simplest models assume, or they will find the deviations in void shapes and expansion rates that would indicate something more dynamic and more complex. The stakes of that distinction are not academic. A cosmological constant is, in principle, explicable as the vacuum energy of quantum fields, though the predicted and observed values differ by a factor so large that the discrepancy is itself one of the deepest unsolved problems in phi. Theoretical physics. A dynamical dark energy field would require entirely new physics, new fields, new particles, and a new theoretical framework to describe them. The resolution of that question may well come from the careful measurement of shapes in the dark. Cosmic voids are the best tools humanity possesses for measuring dark energy. But the nearest and largest of them, the KBC void, is not only a laboratory, it is also distorting everything we see from inside it. If the surrounding environment determines much of a galaxy's fate, then what is shaping our own? Every galaxy in the observable universe grew up somewhere. That somewhere the specific density, temperature, and gravitational environment into which a galaxy was born and within which it spent the billions of years of its development is not a neutral backdrop. It is an active participant in the galaxy's history, shaping its structure, its stellar population, its gas content, its rate of development, and the ultimate form it will take as it ages. Two galaxies that began with identical masses and identical initial conditions can evolve into dramatically different objects if one spent its life in the crowded interior of a galaxy cluster, while the other developed in the near isolation of a cosmic void. The environment does not merely influence the outcome. In many respects, it determines it. This distinction has produced what researchers have come to think of as two fundamentally different civilizations of galaxies, separated not by any cultural or historical boundary, but by the accident of where in the cosmic web each galaxy happened to form. Galaxies in the dense filaments and cluster nodes of the cosmic web live crowded, turbulent lives. Their neighborhoods are busy with gravitational interactions, close encounters with neighboring galaxies that distort their shapes, warp their spiral arms, and pull streams of gas out into the intergalactic medium. Mergers are common events in cluster environments, and mergers are transformative. When two comparably sized galaxies collide and combine over hundreds of millions of years, the result is typically an elliptical galaxy, a smooth, featureless, roughly spheroidal system that has lost the organized rotation and the beautiful spiral structure of its progenitors. The violence of the merger compresses gas into dense clouds, triggering a burst of rapid star formation that consumes the available fuel in a cosmologically brief interval. After the burst, the merged galaxy often settles into a state of low activity. Its gas exhausted, its star formation largely quenched, its population dominated by old red stars, slowly cooling toward the end of their lives. Beyond direct mergers, cluster galaxies face additional environmental pressures that accelerate their evolution and deplete their resources. As a galaxy moves through the hot diffuse gas that fills the space between galaxies, in a cluster gas heated to temperatures of tens of millions of degrees by the gravitational energy of the cluster itself, the ram pressure of that passage strips cold hydrogen from the galaxy's outer disk, like wind tearing leaves from a tree moving at speed. Tidal forces from neighboring galaxies pull at the outer regions of a galaxy's dark matter halo, truncating and distorting the structures that would otherwise extend far beyond the visible disk. The combination of these processes over billions of years produces a galaxy population in dense environments that is dominated by passive, gas-poor, morphologically disturbed systems, galaxies that have been processed by their environment into a state far removed from the pristine condition in which they formed. Void galaxies experience almost none of this. In the interior of a cosmic void, the distances between neighboring galaxies are so vast that close gravitational encounters are rare events rather than the norm. Mergers between comparably sized systems happen infrequently, if at all, over the billions of years of a void galaxy's history. There is no hot intracluster gas to strip the outer disk. There are no dense clusters of neighbors whose tidal fields could truncate the dark matter halo. A void galaxy develops largely in isolation, governed by its own internal physics, rather than by the external forces that dominate in dense environments. The result is a galaxy population that looks strikingly different from what inhabits the filaments and nodes. Void galaxies tend to be smaller in mass than their counterparts in dense regions, a consequence of having undergone fewer mergers and having had less access to the streams of infalling matter that build up mass in cluster environments. They are disproportionately late type systems, spiral galaxies, and irregulars rather than the ellipticals that dominate cluster cores, because the violent mergers that transform spirals into ellipticals have simply not occurred with the same frequency. Their morphologies are often remarkably undisturbed smooth disk profiles, regular spiral arms, rotation curves that show none of the asymmetries produced by tidal distortion. A void spiral galaxy observed in detail often looks as though it has barely aged since it first assembled its structure, preserved by the absence of the environmental harassment that would otherwise have reshaped it. This preservation extends to the most cosmologically important resource a galaxy possesses: its gas. Neutral hydrogen gas is the raw material from which stars are made. A galaxy that retains large reservoirs of cold hydrogen has the potential to form stars for billions of years into the future. A galaxy stripped of its gas is a galaxy whose star-forming lifetime is over. In dense environments, the multiple stripping mechanisms described, above ram pressure, tidal interactions, the cutting off of fresh gas inflow by the hot cluster medium, act in combination to exhaust a galaxy's gas supply over cosmic S. Timescales. Void galaxies shielded from all of these processes by their isolated locations retain far more of their original gas. Many void galaxies are among the most gas-rich systems known, carrying proportionally larger reservoirs of neutral hydrogen than comparable galaxies in denser environments. Here the story produces one of its more counterintuitive twists. Void galaxies have more fuel for star formation, yet their overall rates of star formation tend to be lower than those of their counterparts in active environments. The explanation lies in the distinction between having fuel and having the conditions needed to ignite it. Gas does not spontaneously collapse into stars. It requires a compression event, a shock wave, a gravitational disturbance, to the pressure front from a passing galaxy to push a region of gas above the density threshold at which gravity can take over and drive collapse to stellar ignition. In the busy environments of filaments and clusters, these triggering events are frequent. Mergers compress enormous quantities of gas, simultaneously producing the starbursts that generate a significant fraction of the stellar mass in the universe. Tidal interactions disturb gas distributions, seeding new instabilities. Even the ram pressure that ultimately strips gas from a galaxy can, in its early stages, compress the gas enough to trigger star formation before the stripping begins. In a void, these triggers are absent. The gas sits in extended, stable reservoirs, undisturbed, and waiting for a compression event that may take far longer to arrive or may never arrive at all through external means. Star formation in void galaxies proceeds through internal processes, the spontaneous gravitational instabilities that develop in rotating gas disks, the slow spiral density waves that move through the disk and gently compress gas clouds along their path. These internal mechanisms sustain a steady, moderate rate of star formation, but rarely generate the violent bursts that cluster mergers can produce. The consequence traced across billions of years of evolution is that void galaxies are chemically younger than their denser environment counterparts. Stars create heavy elements through nuclear fusion and distribute those elements into the surrounding gas when they die. Over successive generations, a galaxy's gas grows progressively enriched with elements heavier than hydrogen and helium. A galaxy that has formed stars rapidly across many generations will have gas with high metallicity, a high proportion of these heavier elements. A galaxy that has formed stars slowly, as void galaxies tend to do, will have lower metallicity gas, reflecting fewer generations of stellar processing. Observations of void galaxies confirm this pattern. Their gas is on average less metal-enriched than that of comparable galaxies in dense regions, a direct chemical signature of their more leisurely evolutionary history. What does this mean for the Milky Way, which resides not in the core of a dense cluster, but within the relative quiet of the KBC void? Our galaxy is a large, well-formed spiral, not a disturbed elliptical, not a gas-stripped passive system. It retains enough gas to continue forming stars for billions of years. Its spiral arms are intact and regularly structured. Andromeda, our large neighbour, is similarly a massive spiral system, and while the two galaxies are on a collision course that will result in a merger in approximately 4 to 5 billion years, they have spent most of their histories developing in relative isolation from the kind of dense cluster, environment that would have accelerated and disrupted their evolution long ago. The question this raises is speculative, but not unreasonable. The formation of the solar system roughly 4.5 billion years ago required a stable, relatively undisturbed region of the Milky Way's disk, where gas could collapse and fragment into a star surrounded by a protoplanetary disk, without being disrupted by tidal forces or stripped by ram pressure. The subsequent 4.5 billion years of planetary evolution, culminating in the emergence of life and ultimately technological civilization, required a stable stellar system in a stable galactic environment, conditions that the interior of the KBC void may have helped provide by reducing the frequency of disruptive gravitational encounters that denser environments routinely deliver to their member galaxies. This is a hypothesis, not a conclusion. The connection between void location and the emergence of life involves too many intermediate steps and too many unknown variables to support a definitive claim. But the chain of reasoning is coherent. The KBC void created an environment in which the Milky Way developed with less environmental disruption than it would have experienced in a denser region, which contributed to the preservation of the conditions that eventually made this solar system possible. Our existence may be connected through a long chain of contingent circumstances to the same quantum fluctuation that seeded this void 14 billion years ago. We have established that the void may explain why our cosmic measurements are skewed. But the genuinely larger question is this: if the void is growing, then what does the future of the universe actually look like? If every structure in the universe has an expiration date, how long do you think remains before it expires? There is a peculiar distinction that belongs to the era in which we happen to exist. Not the era of human civilization, not the 10,000 years since agriculture, not the few centuries since the scientific method, not the handful of decades since the first radio telescopes turned their faces to the sky. The distinction belongs to a broader epoch measured in billions of years that cosmologists sometimes call the stelliferous era. The period in cosmic history when stars burn, galaxies are active, and the large-scale structure of the universe has reached something close to its maximum complexity. We are living near the peak of that complexity. The cosmic web, the vast network of filaments, walls, nodes, and voids that we have spent the previous two acts tracing from its quantum origins to its present form, is right now approximately as intricate as it will ever be. The gravitational instabilities seeded by inflation have had 14 billion years to amplify. The filaments have grown thick with matter drawn from surrounding voids. The nodes at their intersections host galaxy clusters containing thousands of galaxies, superheated gas, glowing at temperatures of hundreds of millions of degrees, and supermassive black holes billions of times the mass of the Sunday. The voids have been hollowing themselves out for billions of years, pushing matter toward their boundaries, deepening and widening with each passing era. This is the universe at something close to its structural apex. What follows from here is not stasis. It is not the continuation of the same dynamics at the same pace. What follows is slow, irreversible dismantling. The mechanism of that dismantling is the same force that has been quietly winning its competition with gravity throughout the previous act, dark energy. In galaxy clusters and dense nodes, gravity holds structures together despite dark energy's outward pressure, and will continue doing so indefinitely. The gravitational binding energy of a massive cluster is for now more than sufficient to resist the expansion of the space it occupies. But the clusters are not the whole of the cosmic web. They are the densest nodes in a network whose connecting threads, the filaments and walls, are held together far more loosely, and whose intervening voids are held together not at all. As dark energy continues driving the accelerating expansion of space, the filaments will feel it first. Matter that was once flowing along filamentary channels toward dense nodes will find the distances it must cross increasing faster than it can traverse them. Streams of infalling gas and dark matter that have been feeding the growth of galaxy clusters for billions of years will thin and eventually cut off, starving the structures at the nodes of their supply lines. The filaments themselves, never as gravitationally bound as the clusters they connect, will begin to disperse. Their constituent galaxies, no longer channeled by the filamentary potential well, will drift apart their paths, increasingly dominated by the expansion of the space between them rather than the gravitational geometry of the web. The peripheral galaxy groups those small collections of a few dozen galaxies that sit at the edges of larger structures, bound loosely enough that dark energy can, over sufficient time, overcome their internal gravity, will be the first to dissolve as coherent systems. Within roughly 100 billion years, the organizational logic of the cosmic web will have degraded to the point where it no longer functions as a web in any meaningful sense. What had been a connected network of structures spanning hundreds of millions of light years will have become a collection of isolated islands, each gravitationally bound cluster or group separated from every other by distances that expand faster than light can cross them. Consider the analogy of continental drift. The continents of Earth are moving at rates of a few centimeters per year, fast by geological standards, imperceptible by any human experience of time. A person standing anywhere on the planet cannot feel the motion beneath their feet, cannot observe in a lifetime any change in the arrangement of the land masses, cannot experience the drift as anything other than an abstraction. Yet the process is real, relentless, and beyond any human capacity to reverse. The Atlantic Ocean was not always there. The Himalayas did not always stand as high as they do. The future arrangement of Earth's surface is already written into the physics of the mantle, even if no one alive will ever see it. The destination is determined. The journey is simply too slow for any individual consciousness to witness from beginning to end. The unraveling of the cosmic web operates on the same logic of imperceptibility at human scales, combined with inevitability at cosmic scales, magnified by factors that make continental drift seem rapid. The filaments thinning over the next tens of billions of years will not be visible to any observer over the course of a civilization's history. The isolation of galaxy clusters will not be an event anyone witnesses. It is a condition that will simply at some point have become true without any detectable transition moment. But think carefully about what that isolation means, and a scenario emerges that is both precise in its physics and quietly unsettling in its implications. Imagine a civilization arising billions of years from now on a planet orbiting a red dwarf star. Red dwarf stars are the longest-lived objects in the universe, the smallest and coolest of hydrogen-fusing stars. They burn their fuel with such extraordinary economy that the most long-lived among them will remain on the main sequence for 10 trillion years or more. A civilization arising on such a world, say 10 trillion years from now, would inherit a sky almost unrecognizable by the standards of any human astronomer. Their galaxy, let us say, it is the remnant of what was once the Milky Way, and Andromeda, long since merged into a single elliptical system, would be there, its stars visible, its structure familiar. Everything else that human telescopes once catalogued, the Virgo cluster, the Perseus cluster, the thousands of galaxy groups scattered across what was once the observable universe, would be gone, not destroyed, simply beyond any observational horizon, separated by expanding space, moving faster than light, leaving no signal, no echo, no trace. Their sky would contain one galaxy. Their universe, to all observational purposes, would contain one galaxy. Their cosmic microwave background radiation, the ancient thermal afterglow of the Big Bang that human astronomers measured so precisely with the Planck satellite, would have been redshifted by the intervening expansion to wavelengths so enormous that no conceivable instrument could detect them. The signature of the Big Bang would be in any practical sense gone. The cosmology that civilization would construct, working with the data available to them, would face constraints that no amount of intelligence or observational sophistication could overcome. Their universe would appear static, or nearly so. Their single galaxy would seem to be all that exists. Their instinct perfectly reasonable, given their evidence might well be to conclude that the cosmos is eternal and unchanging, a permanent solitary structure that has always been and will always be. They would have no way of knowing that their galaxy is the gravitationally bound remnant of what was once a web of structures spanning billions of light years. They would have no access to the evidence that would reveal the Big Bang, the expansion history, the original distribution of matter across the cosmos. Their physics would be complete within its domain. Their cosmology would be from the inside, coherent and satisfying. It would also be missing nearly everything that actually happened. This thought experiment has a reflexive edge. The cosmological situation of that future civilization working from incomplete observational access to a universe that was once far richer in accessible information is not entirely unlike the situation of human cosmologists working before 1929, when Edwin Hubble demonstrated that the nebulae scattered across the sky were in fact independent galaxies and that they were receding. Before that demonstration, the dominant cosmological view held that the universe was static, eternal, and contained within the Milky Way. The available data supported that view. The data was simply incomplete in ways that were not visible from inside the limitation. The future civilization's predicament would be the same limitation, imposed not by the inadequacy of their instruments, but by the physics of an accelerating expansion that has placed most of the universe permanently beyond their reach. They would not be less intelligent, less scientifically rigorous, or less sophisticated than we are. They would simply be observing a universe that has hidden most of its history behind a horizon that nothing, not light, not radio waves, not gravity waves, not any signal traveling at any speed can ever cross in their direction again. The universe is not only erasing its structure, it is erasing the evidence of its own existence. And we happen to have been born at the precise moment in cosmic history when that evidence is still visible, still measurable, still available to anyone with a telescope, and the patience to look carefully enough. The universe is not only erasing its structure, it is erasing the evidence of its own existence, and we happen to have been born at exactly the moment when the full picture is still visible. If space is expanding faster than light can travel, then what does observable actually mean? The word observable carries a weight in cosmology that it does not carry in ordinary usage. When someone describes a room as observable, they mean that a person standing in it can in principle see everything in it by looking around. Observability in everyday life is limited by practical things, line of sight, lighting conditions, the finite range of human vision. These are limitations that can in principle be overcome with better tools. A brighter light, a longer ladder, a more sensitive camera. The limitations are circumstantial, not fundamental. The cosmological horizon imposes a limitation that is not circumstantial. It is written into the geometry of space-time by the same physics that governs everything else about the universe, and no improvement in technology, no matter how radical, can overcome it. To understand why, consider what the expansion of space actually does to light traveling through it. When a photon leaves a distant galaxy and begins its journey toward us, it travels through space at the universal speed limit, 300,000 kilometers per second, the speed of light. But the space it is traveling through is not static, it is expanding. The distance between any 2 points in the universe that are not gravitationally bound to each other increases over time, not because those points are moving through space, but because space itself is stretching. A photon making its way across 1 billion light-years of expanding space must cover not just the distance that existed when it was emitted, but all the additional distance that expansion adds while the photon is in transit. For most of cosmic history, this expansion was decelerating. Gravity was slowing it down, and light emitted from anywhere in the observable universe could eventually reach us given enough time. But roughly 5 billion years ago, dark energy crossed a threshold. Its outward pressure began outpacing the inward pull of gravity on the larger scales, and the expansion of space stopped decelerating and began accelerating. The consequence of this acceleration played out to its logical conclusion is that there exists a boundary in space, beyond which the expansion is already proceeding faster than light can travel. A photon emitted at that boundary today aimed directly at us would make no progress. The space between us and its source would grow faster than the photon could cross it. That photon would never arrive. This boundary is the cosmological event horizon. Everything beyond it has already, in a physically meaningful sense, severed its connection to us. Light emitted there today will never reach here. Light emitted there in the past and currently in transit is fighting an increasingly unfavorable battle. The distance it must cover grows faster than it shrinks. Eventually, even those photons in transit will be overtaken by the expansion and stop making progress toward us. What is currently outside the cosmological event horizon is a matter that depends on the precise value of dark energy's strength and behavior. But the current best estimates based on the value of the cosmological constant, derived from supernova and cosmic microwave background observations, place the event horizon at a distance of roughly 16 billion light-years from us. Today, The observable universe, the volume from which light has had time to reach us, since the Big Bang extends to approximately 46 billion light-years in all directions, owing to the expansion that has occurred since that ancient light was emitted. The gap between these two numbers represents the volume of space from which we are already receiving the last photons we will ever receive. Every galaxy in that shell of space between 16 and 46 billion light-years away is sending us its final messages, and we will never hear from those galaxies again. The implication for the future is straightforward to state and difficult to fully absorb. As the universe continues expanding and accelerating, the cosmological event horizon will recede, not in the sense of moving away from us, but in the sense that the galaxies currently inside it will one by one have their recession velocities exceed the speed of light as the space between us and them accumulates more and more expansion. Those galaxies will cross the horizon and vanish from the observable universe. Not because they cease to exist, they will continue burning stars and evolving normally, entirely unaware of any horizon, but because the universe will have placed them beyond any possibility of communication or observation from our position. The timescale on which this process effectively completes is several trillion years. Well before that point, every galaxy outside the local group will have crossed the horizon and disappeared. The Andromeda Galaxy, our nearest large neighbour, currently on a collision course with the Milky Way, that will result in a merger in approximately 4 to 5 billion years, will be incorporated into our gravitationally bound system before the horizon can swallow it. The other members of the local group, the Magellanic Clouds, the dwarf galaxies scattered through the local group's volume, will similarly remain bound to the merged system by gravity, which holds these structures together against the expansion. But the Virgo cluster, roughly 53 million light-years away, and the nearest major cluster outside our local volume, is already beyond the gravitational reach of the local group. It will not be absorbed. It will drift and eventually cross the horizon. What remains is a single gravitationally bound island, the merger product of the local group's major galaxies, adrift in a void of its own creation, surrounded by expanding emptiness that extends to infinity in every direction and contains nothing reachable by any signal. No neighbour, no context, no reference point beyond the structure itself. In this future, the cosmic microwave background, the ancient thermal radiation that encodes the conditions of the universe 380,000 years after the Big Bang, the signal that the Planck satellite measured with such the extraordinary precision, the evidence from which human cosmologists derived the age and composition of the universe, will no longer be measurable. Every photon of that radiation has been travelling for nearly 14 billion years, growing cooler and redder as the universe expands. Currently, its temperature is 2.7 Kelvin, cold but detectable. As expansion continues over hundreds of billions of years, those photons will be stretched to wavelengths longer than any conceivable instrument could resolve, and their temperature will drop toward values indistinguishable from absolute zero. The signal will not be switched off. It will be diluted past any threshold of detection, smoothed into a uniformity that carries no information because no instrument can resolve its fluctuations. The Big Bang will, in the deepest observational sense, have never happened. Not because the history will have been undone, but because every record of that history will have been written on a medium, the spectrum of the cosmic microwave background, that expansion will have rendered permanently unreadable. This is what physicists sometimes call the information horizon problem, and it is distinct from the technical challenge of building better telescopes. No telescope, regardless of its sensitivity, can detect a signal that expansion has stretched to wavelengths larger than the observable universe itself. The information was real. It was encoded in the universe. It is being systematically erased, not by any catastrophic event, but by the patient geometric consequence of space expanding faster than light can carry meaning across it. The universe is at this moment forgetting what it is. Every billion years, more of the evidence disappears. Every galaxy that crosses the cosmological horizon takes its history with it, inaccessible to any observer on the other side. Every increment of redshift added to the cosmic microwave background strips another layer of resolution from the record of the Big Bang. The process is not violent. It produces no light, no shockwave, no detectable event. It is simply the accumulation of silence, the steady conversion of accessible history into unreachable past. We currently observe from inside the KBC void, which already biases some of our measurements and complicates some of our interpretations. But the observation is still possible. The light still reaches us. The cosmic microwave background is still detectable, still measurable, still carrying the information that allows human cosmologists to reconstruct the first 380,000 years of cosmic history from a signal emitted nearly 14 billion years ago. That access is not guaranteed. It is a function of when, in cosmic history, we happen to exist, and we exist by the standards of the universe's lifespan, at almost the last moment when the full picture is still technically visible. Future civilizations, if they arise at all, will inherit a cosmologically impoverished sky. They will have access to one galaxy's worth of information about a universe that once contained hundreds of billions. They will have no way of detecting the signal that would tell them a Big Bang occurred. They will have no way of knowing that the structures we have mapped, the filaments, the walls, the clusters, the voids, the entire cosmic web that required 14 billion years of gravitational work to assemble, ever existed. We are the last observers for whom the full record is readable. But before the universe erases the last traces of itself, it leaves behind a question that science has not yet answered, and that question may be the most important one in the history of human thought. If the foundation of every cosmological equation is built on an assumption that has not been fully verified, how trustworthy are the conclusions drawn from those equations? Every field of science rests on foundational assumptions premises, so basic, so load-bearing, that the entire theoretical architecture above them depends on their stability. In structural engineering, you can inspect the foundations of a building. You can drill into them, test their composition, measure their load tolerance. In cosmology, the foundations are mathematical and philosophical, and testing them requires observing a universe that does not hand out inspection certificates. The cosmological principle is the deepest foundation of modern cosmology. It states in its simplest form that the universe is homogeneous and isotropic when viewed at sufficiently large scales, the same in every place, the same in every direction. Homogeneous means that no location in the universe is fundamentally different from any other. Isotropic means that looking in any direction from any point reveals statistically the same picture. Together, these two properties describe a universe that has no center, no edge, no preferred axis, and no special locations. The cosmos from high enough above is smooth. This principle is not merely an aesthetic preference. It is the mathematical precondition for virtually every equation in modern cosmological theory. The Friedmann equations, which describe the expansion of the universe and govern everything from calculations of the Hubble constant to estimates of the universe's age, are derived under the explicit assumption that the cosmological principle holds. Models of structure formation, calculations of the cosmic microwave background power spectrum, predictions of the abundance of light elements from Big Bang, nucleosynthesis, all of these depend at their foundations on a universe that is at the relevant scales smooth. A universe that violates the cosmological principle at those scales does not merely require adjustments to the models. It requires the models to be rebuilt from a different starting point. The cosmological principle was never intended to apply at small scales. Obviously, the universe is not homogeneous at the scale of a solar system, a galaxy, or even a galaxy cluster. Structures of every conceivable size and density exist at those scales, and no one disputes this. The claim is specifically about large scales, scales large enough that local irregularities average out, and the global smoothness of the universe becomes apparent. For many decades, the theoretical consensus held that this averaging would occur at scales of a few 100 million light-years. Above that threshold, the argument went the universe should look essentially the same from any vantage point. The KBC void challenges that consensus directly, and it does so not through theoretical argument, but through observation. A void, approximately 2 billion light-years in diameter, containing matter at roughly 20% below the cosmic average density, centered on our own position in the cosmos. This is a structure that exists at a scale where, according to the standard model of cosmology, the universe should already be homogeneous. 2 billion light-years is not a local irregularity. It is not a small wrinkle in an otherwise smooth fabric. It is one of the largest coherent underdensities that has been identified in the observable universe, and it sits precisely where we are. If the cosmological principle holds cleanly at the scales, the standard model assumes structures of this size, and depth should be exceedingly rare. Some analyses suggest they should almost never occur within the framework of the standard cosmological model. The KBC void is not the only structure raising these questions. The field has accumulated other examples of large-scale organization that strain the boundary of what the cosmological principle predicts. The Sloan Great Wall, identified in 2003, is a filamentary structure approximately 1.4 billion light-years in length. The Hercules Corona Borealis Great Wall, reported in 2013 and subsequently refined through additional observations, is estimated to span approximately 10 billion light-years, a scale so vast that if the measurement is confirmed to full precision, it would represent an organization of matter that the standard model has no comfortable mechanism to produce. At 10 billion light-years, we are not talking about a local anomaly. We are talking about a structure whose existence at that scale is in direct tension with a universe that should have smoothed itself out well below that threshold. Two interpretations present themselves, and neither is comfortable. The first is that the scale at which the cosmological principle applies is simply larger than cosmologists have assumed. Perhaps the universe does become homogeneous, but only at scales of several billion light-years rather than several hundred million. If this is true, the principle itself survives, but its domain of applicability shifts. The practical consequence is that many calculations in cosmology have been performed assuming the universe was smooth at scales where it was not, and the results of those calculations carry systematic errors that have not been fully accounted for. The Hubble tension, the apparent anomalies in large-scale structure statistics, the difficulties with the KBC void in simulations, all of these could be downstream effects of applying the cosmological principle at scales too small for it to actually hold. The second interpretation is more fundamental. The cosmological principle may be a useful approximation rather than a literal truth about the universe. Not wrong in a way that invalidates everything built on it, but incomplete in the way that Newtonian mechanics is incomplete. Accurate enough for most purposes within a defined domain, but yielding to a more complete description when pushed beyond the edges of that domain. In this interpretation, the principle is a scaffold that allowed cosmology to develop into a precise quantitative science, but the scaffold is not the building. The universe may have structure at scales that the principle taken literally should not permit, and accommodating that structure may require adding a layer of positional context to cosmological calculations that has historically been omitted. The consequences of this second possibility, if it proves correct, cascade through the entire framework of modern cosmology. Calculations of the universe's age, currently placed at approximately 13.8 billion years, depend on the Hubble constant and on the cosmological model, both of which are built on the principle. Estimates of the proportions of ordinary matter, and dark energy in the universe's total energy budget are derived from fitting the cosmological model to observational data, assuming the principle holds. The interpretation of the cosmic microwave background's temperature fluctuations, the analysis that produced the precise compositional estimates that Planck reported, uses the principle as a baseline assumption throughout. None of these results would necessarily be overturned by a cosmological principle that turns out to be an approximation rather than an exact truth, but they would need to be reconsidered with that approximation's limitations explicitly built into the analysis. It is important to be precise about what this does and does not mean. Recognizing that a foundational assumption has limits is not the same as discovering that everything built on that assumption is wrong. The history of science is full of cases where a foundational principle was refined, generalized, or found to have a restricted domain of validity, and where the refinement made the science more powerful rather than less. Newtonian gravity was not wrong. It was incomplete. General relativity did not erase everything Newton had built. It incorporated Newtonian mechanics as a special case, valid within a defined set of conditions, and extended the framework beyond those conditions into new territory. The same process, if the cosmological principle is found to be an approximation, would strengthen cosmology rather than undermine it. A model that explicitly accounts for large-scale inhomogeneities, that includes our position inside the KBC void as a measurable parameter, rather than an unexamined background condition, would be a more accurate model than the one we currently use. Its predictions would be better calibrated. Its systematic errors would be smaller. The Hubble tension, which currently sits as an unexplained anomaly demanding exotic new physics, might resolve into a predictable consequence of our specific location. Not a crack in the foundations, but a measurement artifact that a more complete model would naturally absorb. Science progresses, not by defending its foundational assumptions against all challenge, but by testing them, finding their limits, and building the next framework at the boundary where the previous one stops working cleanly. The cosmological principle has been one of the most productive, foundational assumptions in the history of science. The fact that it may have limits, that the universe may have structure at scales beyond where the principle says it should, is not a failure of the principle. It is the principle doing its job, holding long enough for cosmology to mature into a field sophisticated enough to test it. And if our position in the universe turns out to be genuinely unusual, then a question follows that no one has yet had the standing to ask clearly. And if our location in the universe is genuinely unusual, that raises a question nobody has dared to ask aloud. Could that be anything other than a coincidence? If the existence of life depends on a series of rare conditions, what does it mean that a mind capable of asking this question exists at all? Throughout these 3 acts, we have been examining the universe from the outside in, tracing the origin of emptiness from quantum fluctuations, following the growth of voids through gravitational amplification across billions of years, confronting the future in which dark energy carries that emptiness to its final total dominance. We have treated the void as the subject and ourselves as the observers. But at this final point in the story, that framing needs to be inverted completely. The voids are not the unusual feature of the universe. We are. This inversion is not a rhetorical gesture. It follows directly from the numbers that have appeared throughout this story and from the trajectory of cosmic history that the physics demands. Consider the universe at 3 distinct moments: its beginning, its present, and its far future. At the beginning, in the first fractions of a second after the Big Bang, before inflation had even finished imprinting its quantum signature onto the fabric of space-time, the universe was to an extraordinary degree of precision uniform. The density variations that inflation left behind were deviations of 1 part in 100,000 from the mean. If you had sampled any 2 regions of the early universe and compared their energy densities, you would have found them essentially identical. The cosmos was at the moment of its seeding almost perfectly smooth. No structures existed. No concentration of matter had yet assembled itself into anything that could be called a thing rather than a region. The universe was from any reasonable perspective closer to empty than to full not empty, in the sense of containing nothing, but empty in the sense that nothing distinct had yet differentiated itself from anything else. In the far future, after the cosmic web has fully unraveled, after every galaxy outside the local group has crossed the cosmological event horizon and vanished from the reachable universe, after dark energy has achieved its final and absolute victory over the gravitational bonds that once connected structures across hundreds of millions of light years, the universe will again be, from any accessible vantage point, essentially empty, not of matter. The matter will still be there, locked inside the gravitationally bound remnant of the local group, burning slowly in the long-lived stars of a merged elliptical galaxy, but empty of relationship, empty of structure, empty of the connections between things that give a cosmos its shape. One island in an infinite accelerating void with no neighbours reachable in any direction at any speed for any duration. Functionally, observationally, cosmologically empty. Before structure, after structure. The universe's default state, its ground state, the condition it begins in and returns to, is emptiness. The present is the anomaly. The cosmic web, for all its grandeur, for all the billions of years of gravitational labour that assembled it, represents a temporary departure from the universe's baseline condition. The filaments and clusters and walls are not the natural state of matter in the cosmos. They are a transient excursion, an interval measured in tens of billions of years, against a cosmic history that extends to timescales of trillions and beyond, during which gravity managed to overcome the baseline tendency toward uniformity and emptiness and build something complicated. That interval is happening now. We are inside it. We are, in a precise and non-metaphorical sense, living during the brief structural flourishing of a universe that spent its early history too hot and too uniform to form anything, and will spend most of its remaining history too cold and too dispersed to hold anything together. And within this temporary anomaly of structure within the transient complexity of the cosmic web, the places where life can arise constitute a further narrowing, another layer of rarity stacked on top of the first. Life, as far as we know it with any confidence, requires specific conditions. A star of the right mass, burning at the right temperature, stable enough to illuminate a planet for billions of years without sterilizing it. A planet in the right orbital range with the right mass to hold an atmosphere with liquid water at the surface, with enough chemical complexity in its crust and oceans to support the emergence of self-replicating chemistry. A galactic environment stable enough that the planet is not regularly bombarded by the radiation of nearby supernovae or disrupted by close gravitational encounters with passing stars. The conditions are many, and each one narrows the available parameter space further. The universe's volume may be effectively infinite. Current models suggest the full universe extends far beyond the observable horizon, possibly without limit, but the fraction of that volume where conditions suitable for life currently exist is genuinely measurably small. We occupy one such place. The Milky Way, developing within the relative quiet of the KBC void, accumulated the conditions that made this solar system possible. The solar system, forming in a stable region of the Milky Way's disk, produced a planet with the right mass and the right chemistry and the right orbital distance. That planet, over 4.5 billion years, developed life that grew complex enough to build telescopes, process redshift surveys, map the cosmic microwave background, identify the KBC void, and assemble the argument you are currently reading. That chain of contingency, quantum fluctuation to void, to galaxy, to solar system, to planet, to life, to consciousness, to question, is not a chain that operates in most of the universe. Most of the universe is the interior of a cosmic void, where matter density is too low for gravitational processes to have assembled anything as complex as a galaxy cluster, let alone a solar system, let alone a planet, let alone a mind. Most of the universe is the expanding space between filaments, where no filaments have managed to thread themselves, and no nodes have accumulated the matter needed to form even modest galaxy groups. Most of the universe right now is already beyond the cosmological event horizon of every observer that exists unreachable, unobservable, effectively outside the causal structure of any accessible reality. We are not looking at the universe from a position of cosmic neutrality. We are the rare exception that gravity managed to produce during the brief window between the universe's undifferentiated beginning and its undifferentiated end. The emptiness is the rule. The complexity is the deviation. This does not diminish the existence of anything. If anything, the correct response to this framing is the opposite of diminishment. In a universe where 90% of the volume is void, where the default condition of matter is dispersal rather than concentration, where the baseline trajectory of every structure is toward dissolution and isolation, the existence of a place where matter has organized itself into something complex enough to perceive its own situation is not a small thing. It is, by the statistical standards of the cosmos, an extraordinary deviation from everything the universe ordinarily does. The specific strangeness of our position inside the KBC void adds another layer to this. We are not just living in a universe that is predominantly empty. We are living inside a particularly deep underdensity within that universe, a region where matter density runs 20% below the cosmic average, where the conditions for structure formation are less favorable than in the dense filaments where the void itself contributed to the formation of our galaxy by providing an environment of reduced gravitational disruption. The same underdensity that biases our measurements of the Hubble constant, that sits at the boundary of what the cosmological principle predicts should exist, that challenges the standard model's assumptions about large-scale homogeneity, that same underdensity may be part of the chain of circumstances that made this planet possible. We are not observers standing outside the universe, examining it with detached neutrality. We are part of the exception, one of the rare concentrations of matter, complex enough to perceive the rule looking outward at the overwhelming majority condition from which our existence represents an improbable departure. The rule is silence. The rule is darkness. The rule is the vast, cold, expanding emptiness that constitutes the volume of the cosmos. We are what happens when the exception in one small corner manages to look back at the rule long enough to understand it. The universe does not need us to exist. It was empty before structure formed, and it will be empty again long after the last star has cooled. But without us, without some arrangement of matter complex enough to perceive, to measure, to reason, and to ask, there would be nothing in the universe that knew it was empty. The void would expand forever, without a single point of observation from which its expansion could be noted. The cosmic web would have assembled and dissolved across tens of billions of years without leaving any record in any mind. The quantum fluctuation that seeded the KBC void 14 billion years ago would have grown to 2 billion light-years of underdensity, and the universe would have been thoroughly unaware of the fact. The universe is not only erasing its structure, it is for one brief interval in its history capable of knowing that. That interval is now. And in the moment you recognize that the mind is observing its own absence across most of the universe, that is the strangest and most astonishing thing science can ever deliver.